repeated doubling. If you were asked to start with the number 5 and double it 3 times, how could you write that problem out using math notation? How could we write that? Uzziah, you want to try? Not 5 squared. Does start with 5 though. How do you double 5 just one time? How do you double 5? Connor? Times it by 2, right? Take out your earpod for me. Yeah, we times it by 2. But if we want to times it by 2 3 times, then we multiply it by 2 3 times. That's all that means. All right? Is there another way we can write that? Is that? No, but it'd be 5 times 2 to the 3rd power. But that's not the same as 5 to the 3rd power, right? Right, so this would be equal to 5 times 2 raised to the 3rd power. But you have to start with the 5, and that brings us to something important. When we are writing these exponential or using these exponential equations, the only thing getting raised to the x power is that b, that growth rate. Now, your calculator will do the order of operations for you, so you don't have to distinguish that in any way. Your calculator is going to do it for you. But not all calculators will, so depending on which device you're using to evaluate these exponential functions, sometimes it does matter. If you were asked to start with the number 5 and double it 9 times, then how could you write that? Wouldn't there just be 9 2's there? Would just be 5 times 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. That gets a little bit tedious when these numbers get bigger. I mean, frankly, to the 9th power is too tedious. So we write it 5 times 2 to the 9th power, right? And it becomes very obvious when you get example 3 and that it says, what if you double 5 100 times? Obviously, not only do we not want to write to 100 times, it's impossible to keep up with how many times, or very hard to keep up with how many times we've actually multiplied by 2 in the calculator, right? But we can use the exponential, the exponent button. And on your calculator, if you're using ours, it's the caret button. Do you guys see the caret button on your calculators? It's right below the pi button and right above the x squared button. Will you drop your phone in your backpack, Weston? Did you grab a calculator, buddy? Okay, grab a calculator. If you don't have a calculator, you need one. Harmony, you got one, honey? Did you find the exponent button on there? Okay, that's what I just told you. So look at, it looks like an arrow pointing up. They call it a caret. It's right below the pi button on the left and right above the x squared button. Raise your hand if you found it. Kevin, did you find it?
Yes.
Okay. Kamai, did you find it? All right. If you have a different calculator, I don't know where yours is. It's okay. You can use a different calculator. I'm not going to be an expert on your calculator. I'm pretty good on these calculators, but I'm not going to be able to help you a lot on a different calculator. I can help you on the TI X30A from algebra, or I can help you on this TI. But other than that, you're kind of on your own. I mean, I can try to help you, but I don't know, just sitting here where it's going to be. Summer? The caret button. The exponent button looks like an arrow pointing up. It's called a caret. It's right below the pi button and right above the x squared button on the left. Hand it back to us. All right, so everybody do 5 times 2 to the 3rd power on your calculator. What'd you get, Weston? What'd you get, Joseph? Yeah, you should have gotten 40, right? What'd you get, Hoagie? What'd you get, Cameron? Yeah. 5 times 2 is 10, times 2 is 20, times 2 is 40, right? So try it again. Clear it out 3 times. 5 times 2, the exponent button, the arrow right there, yeah. 3 equals. What'd you get? Yeah, you squared it. I think you squared it right there. Okay. Let's do 5 times 2 to the 100th power. What do you get? What'd you get, Tash? You get a lot? Is that what you're saying? You get a lot. Yeah, it should be in standard notation. Times 10 to the 30th power, right? Yeah. Okay. Caught up with me? Everybody knows where to find your exponent button. All right, so a lot of this that we've talked about already on Friday, we said that an exponential function is this form, y times a times b to the x power, where a is the initial amount or initial value, and b is the growth or decay rate, growth or decay factor. If b is greater than 1, remember anything multiplies something by a number greater than 1, then it makes that number bigger. So that would be the growth. They refer to that as exponential growth. If b is between 0 and 1, that means it's less than 1, but greater than 0. That function will shrink or decrease, however you want to think about it. You could also think about it as decaying. It's referred to as exponential decay. When something decays, it starts going away. If b equals 1, what happens when you multiply a number by 1? What's 1 times 100? It just stays the same. That's right. So it does not change the starting value at all. X is the number of times that you'll be multiplying by b. X is the number of times that you're going to use b as a factor. So we're going to practice using identifying the parts of this exponential function. And so we're going to start with what is the starting value? What is the initial value in this function y equals 3 times 5 to the x power? What's the initial value, Amani? Remember that function looks like this. 3, very good. So that is your A. A is the initial value. And is this, what is the growth or decay factor? It's 5. So remember, that's what is being multiplied by the initial factor. And is it a growth or a decay factor? Growth is greater than 1, so it is a growth. It's growing. Describe in words what this function is doing. So what would we say this function is doing, Ariel? It is growing specifically, though. What would we say? Let's look back at this example here. It says, if you were asked to start with the number 5 and double it 3 times. So that's what's happening here. The initial value is 5, and we're doubling it 3 times. Does that make sense? Or multiplying it by 2 3 times. You could say it that way as well. So how could we describe this one in words? Multiplying what by 5 times? Yeah, so we're multiplying 3 by 5 how many times? Is that what you said? Yeah, x. We don't know how many times, so that is what our input is. So we are going to say that we're starting with 3 and multiplying by 5 x times, or x number of times. And then we're going to plug that into our calculator and see what we get. 5 y equals 3 times 5 to the third power. So we're going to replace x with 3. That is how we solve that. Find the result of x is 3. That means we replace the x in that exponential function with 3. If you're not using our calculator, you do need to remember you have to raise the power before you multiply it by 3, or use parentheses. So it could be 3 times 5 raised to the third power, close your parentheses. But your calculator does it for you. So it would be y equals 3 times 125. But literally, all I care is that you enter it from left to right. So put this in your calculator and give me this. You need to show me this is what you put in the calculator. So if you're asked to evaluate one of these functions for a particular x value, you do need to write that down and then just plug it in your calculator. So far, so good. Any questions? Gives you the same thing here. What's the starting value? What is the growth of your k factor? Y'all can do it on your own, and then we'll go back and make sure you get it right. Need a translator? What did you get for the starting value, Kayla? Good. What did you get for the growth of the k factor, Taj? Would you say if the function is growing or decaying, Kevin? How do you know? Yeah. So remember, so it's going to be less than 1 and greater than 0. So it can't be negative. Can't be 0. So describe in words what this function is doing. Can you tell me what this function is doing, Joseph? There's no 5 there. So remember the last one we said starting with 3 and multiplying by 5x times. If we describe this one that way, what's it starting with? Okay, so starting with 32, and what are we multiplying it by? And how many times? Yes, that's all. Okay. So you were in this one. Got it. Okay, so the result, if x equals 5, just means we plug in, instead of x, we plug in the 5 here, and we plug it in our calculator. So 32 times 0.25, 5 times, or raised to the 5th power. And you can see it's much less than the initial value. Not even close to 1 anymore. It's decayed or reduced or shrunk or decreased, gotten smaller, however you want to think about it. Any questions so far? We do have an exit ticket for 5.2. While I'm thinking about it, it's the 5.2 exit ticket on Amplify. So that and this worksheet will be due tomorrow. This worksheet's not going to take you very long. And the exit ticket on Amplify won't take you very long either. Everybody clear on that? doing the amplified 5.2 exit ticket on, and you're doing this worksheet for homework tonight. Got it? Okay. And we're going to be done with these pretty quick. We'll be able to start whichever one you want. All right. So use what you've learned about the partial exponential functions to write an equation for each of the situations and answer the question. Every time the node lies, his nose doubles in size. His nose is 1.5 inches long before counting any lies. Does everybody know the Pinocchio story, the Disney story? So when you tell the lies, the little wooden boy, whenever you tell the lies, the nose doubles in size. Write an equation that represents this situation where x is the number of lies and y is the size of Pinocchio's nose after x lies. So what do you think? Brooke, can you write the equation, the exponential function for us? So this is the format. Y equals the initial value times the growth rate to the x power. Sorry? That's the start, yeah. So the start is 1.5. What's the growth rate? Yeah, so to double means times 2, right, Brooke? So double means times 2, so the growth rate is 2. So what's the equation going to look like, Brooke? Sorry? I don't know. Look up here. Times 2 to the x power. The only thing we forgot was the x, okay? So use your equation to calculate how long Pinocchio's nose will be after 6 lives. So that just means we're replacing x with 6. So putting that in our calculator. Chuck it in on your calculator, Evan. See what you get. Did you already put it in your calculator, Samaya? Okay. And you got it? Carl, you with us? Do you understand? You're going to do that on your calculator. What'd you get? Use the carrot there, so use the little carrot. Nope. So that's why I was telling you. That's why I wanted you guys to somebody to just know where the exponent is. So this is the exponent. Now cut that, and now finish. So 96 is correct. So again, after 6 lives, his nose will be 96 inches long. All right, well, it's kind of a silly example. What we're going to be using it for is more financial. So we're going to look at this next example. It says you make a $10,000 investment that has historically doubled every 7 years. So we need to clarify something in so for financial problems, we're going to be talking about growth of money, and X is always going to be the time in years. So we need to make sure that we know that. So X would be the time in years. Does that make sense? Now here's the thing. If it doubles every year, then X is just whatever X is. But if it doesn't double every year, we have to create a fraction so it only doubles the number of times it's supposed to. So the beginning value is 10,000, the growth rate is 2 because it doubles. But instead of just putting X, we have to put X divided by 7 because it doesn't double in 1 year. It doesn't double in 2 years. it's not going to double until the 7th year for the first time. Does that make sense? So 7 years, when X is 7, it will have doubled 1 time. When X is 14, it will have doubled 2 times. It will be somewhere less than doubling up to 7 years, sometimes less than quadrupling after that. So that is what that function will look like, that equation will look like. Elder, are you with me? So it says use your equation to calculate the value of the investment after 15 years. So this is our equation, this is our function. It's X divided by 7 here. None of that changes, except that instead of putting X, we have a 15 there. And we can put it in our calculator. You do need to use parentheses around these unless you use the fraction button. So let's go ahead and make a note here. Unless you want to use the fraction button on your calculator, you do need to put these in parentheses. So if you're on your calculator entering this problem, it would be 10,000 times the times button to the caret button, parentheses, 15 divided by 7, close your parentheses. Does that make sense? Does that make sense, Connor? So what did you get when you did that? Summer, have you entered it yet? No, I'm not. Okay. So the 10,000 times button to caret or exponent button, left parentheses, 15 divided by 7, close your parentheses, and then you need your equal button. Let's try it again. I have $44,163. We're rounded to the decimal place. Cleared out 3 times. Let's try it again. I put 18 over 2. Okay, that'll do it. Had somebody first here use the X squared button instead of that caret or the exponent button. All right. Everybody know how we got $44,163.58? So what does that mean? That means after 10 years, when his money doubles every 7 years, it's $44,163.58. That means he deposited $10 one time, and 15 years later, it's already over $40,000. That's pretty great, right? That is exponential growth. That's what we're calling that. That's an exponential equation function. And we can use this formula to find the value of an investment after a certain period of time. We can use this formula to find out how long it will take the investment to reach a certain amount. We can use this formula to find out what the initial investment needs to be for it to earn a certain amount over time, given a particular growth rate. And that's what we're going to kind of talk about here. And there's other types of equations. You can solve exponential functions for any variable. In this section, we will solve for the exact initial value, but only estimate the exponent. Solving for exponents is beyond what we've learned so far. So the formula we have, this exponential equation, we are going to be solving for the initial value, A, and we'll be solving for X, but X will be an estimate. We'll be doing a guess and check strategy versus solving the equation for X. Because we have not learned in none of the math classes probably that you've taken, unless you've taken Algebra 2, you might have solved for that exponent, a variable exponent, but we can solve for the A, and I'll show you how to guess and check and solve for this one. All right, so I make an investment with the goal of having $20,000 after 30 years. If the growth factor is 1.12, how much money will she need to invest to reach her goal? So we're going to go through and identify the A, the B, the X, the Y. So the $20,000 is what she wants the Y to be, what she wants her output to be. So we're going to say Y is 20,000. The time is going to be 30 years. They tell us the growth factor is going to be 1.12. And what we're looking for is how much money she needs to invest so that she can have $20,000 after 30 years, a one-time investment. So what we're going to do is we're going to plug in the parts that they give us. Anybody have a guess? How much money do you think she would need to deposit to have $20,000 in 3 years? Just off the top of your head, what do you think? One deposit, 30 years, and it's going to grow by 12% each year. That's the growth factor. Yeah. What do you think? What do you think? Just off the top of your head. I mean, it's just for fun. Say it again? How much money would she have to deposit? She'd have $20,000 in 30 years. $20? Okay. You said a month? No, it's one time investment. What do you think, Caleb? Off the top of your head. You said $20? $100? What do you think, Weston? Y'all are really optimistic financial investors. It's not a lot, but it's more than that. What do you say? 500? Okay. So let's see. If we start, if we want $20,000 and that goes in our Y spot, we don't know what the initial value is. That's what we're trying to figure out. Times the growth rate raised to 30, right? So the way this one is easy, we can just divide away the 1.2 to the 30th power. Remember, the goal is to get A by itself. So even though it's kind of ugly, we can just anything divided by itself is 1. So if we divide 1.12 raised to the 30th power by that, it simplifies to 1, or that right side would be 1A. Here we can do 20,000 divided by 1.12 to the 30th power. I don't think you have to do any parentheses or anything there. We tried that for the first period. And $667.56 is all you need to deposit one time if you just leave it alone and let it grow exponentially for 30 years. I wish it were $20 or $50, but heck, $667.56, that's a pretty good return, right? All right. So that one's pretty straightforward. You can use algebra pretty easily there. For this one, it says Charlotte has $12,000 to invest, and would like this investment to grow to $18,000. If the growth factor is 1.09, how many years will it take to reach her goal? We are going to use guess and check, and we're going to make this until you get close to the desired. And we're going to say result. And we don't know what the result is yet. We are going to have to do a little bit of algebra. First thing we're going to do is set it up. What is the A in this problem? Do you guys know? What's the A? What's the initial value? That's the initial investment. Joseph? Right. So in this case, figure something there. The A is going to be the initial investment. Anytime we're doing investment problems, A is going to be the initial investment. And B is still going to be the growth rate. And X is going to be the time in years. So $12,000 is the initial value. The growth rate is 1.09. And the X is what we're trying to find out. We want our output. We want our Y to be $18,000. So we just take the things that they give us and plug them into the formula. So instead of Y, it's 18,000. Instead of A, it's 12,000. Instead of B, it's 1.09. So we don't have to guess and check yet. The first thing we're going to do is we're going to get this this factor with the x by itself, and we can do that by dividing both sides by 12,000 first. So 18,000 divided by 12,000 is 1.5. And we know that's going to equal 1.09 times some number, raised to some number of years, right? So this is where the guess and check comes in. So I'm going to switch this around because I don't like it that way. I'm going to do 1.09 to the x equals 1.5, and this is where the guess and check comes in. So let's start with 2. So let's replace x with 2. So 1.09 to the second power. We're going to do that on our calculator and see what that is. Are we close to 1.5 yet? 1.09 raised to the second power. You should get 1.1881, right? So let's see, what if we go up to, what should we try, 3 or 4? Let's try 4. If it's more than 1.5, then we'll know we can come down. So 1.09 raised to the fourth power. Let's see what we get. I got 1.411 and some other decimals. So what y'all got? 115, and I'm going to put dot, dot, dot. So let's see if we can get closer to that. So let's try 1.09 to the fifth power. So that would be 5 years. So I got 1.5386 dot, dot, dot. We have a bunch of other decimals after that. So 1.53 is closer to 1.5 than 1.4115. So we're going to say that it's going to take around 5 years to get $18,000 if you invest $12,000. So that means about 5 years. That's what that little squiggle means. Does that make sense to everyone? 18,000 divided by 12,000. Okay, so if you're looking for a number of years, you just kind of got to simplify as much as you can and then just start plugging in numbers of years. Any questions? In a minute, we're not quite done. All right, so let's get your worksheet out because I did not go over this with first period until after they had started it, and some people were confused, and rightly so. So let's see if I can find where it went. All right, so you should go ahead and get your worksheet out that you picked up today. Remember, you're going to also do the 5.2 exit tickets here in a minute. If you like, you can do that first. Okay. So this explains what I'm going to talk to you about, your worksheet. There is a link here. You should go to that link and watch the video. The growth rate in a financial problem, remember if it's growing, it's going to be greater than 1. So here, looking at the problem they give you, it says y equals the value after 10 years. The initial value, this is a 5% increase in value per year, but you'll notice our growth factor is 1.05. So if we want a value and investment to grow, we want it to keep its initial value, which is 100% of your investment, and we want it to grow by 1%. So the initial $150,000 is 100% of $150,000. Does that make sense, Brady? if we want it to grow 5% more, that's 100% plus 5%, and we're going to turn that into a decimal for the growth rate. If this were a decay problem and it was decreasing in value by 5%, we take that 100% and we subtract 5% and then turn it into a decimal. All right. So make sure you watch the video link there. I'm sure it's not very long. And that will remind you of how to do or explain it a little bit more. Any questions? So the digital copy of the notes is where you can get that link. Right. I'm sorry, the digital copy of your worksheet right here is where you can get that link. All right? So worksheet and